Good morning, scholars of organic chemistry. How you doing today? Hey, we're going to take an in-depth look at orthopara versus meta-directing groups. Let's get a deeper understanding of why some direct orthopara and the others direct meta. We need the mechanism for a more thorough explanation. So let's go back to key concepts. Unit 1, Part 3. It looks like this. You've seen those reactions now. There's 8 of them. They all have a common mechanism. And scrolling down, here we go. Let's take a quick look at that mechanism. There's another video that goes through this mechanism in detail. So we'll just kind of hit the highlights. Step 1, identify the electrophile. So it depends on your reaction, right? So let's scroll up to the all 8 reactions, right? So if you're doing nitration, you're putting the nitro group on. So the electrophile is that group that's going to be added to the ring. Well, I should say substituted onto the ring. If it's the set of reagents, then you're putting on the sulfonic acid group. That's the plan, right? Do bromine. Yeah, we saw that before in the other video. It's Br+. Cool, that's your electrophile. And there is a mechanistic step with curved arrows that explain how these cations form, but on my exams, that's not required. Step 2, add the electrophile to the ring. So given your benzene ring, there'll be 3 pi bonds. And then you decide where your group is going to go. And so if you decide, like I did here, I said, hey, I want bromine to go onto this carbon. Then what you have to do is find the pi bond connected to that carbon. It's right here. And then use a curved arrow that says, hey, these 2 electrons in the pi bond are going to connect to the bromine, and they actually end up here. So the pi electrons actually form this new single bond to the bromine. And this poor carbon, which used to be double bonded, no longer is. It only has 3 bonds, and because it should be bonding 4 times, but only has 3 bonds, that endows that carbon with a positive charge. Okay, that's step 2. Step 3, take that same structure and you can redraw these however you want, whatever you're comfortable doing, right? So that's my philosophy. When you draw a molecule, you decide how to draw it. Okay, and you can see the variety here. I've drawn all the H's in this structure up here, and here I said, nope, don't want to do it. Your choice. Okay, but these 2, hopefully you can see that they are the same structures. And step 3 is draw all the resonance structures. There will be at least 3, and in some cases, there'll be more than 3. But you got to get at least these 3 minimum. For full credit, you got to get them all. So how do you know you're getting them all? I'll show you some examples in a minute. For now, what you need to do is find the nearest pi bond to your reactive center. So in the future, we'll see cations, anions, and radicals that we have to draw resonance structures for. This one's a cation. Our reactive center is a cation. Find the nearest pi bond or a lone pair. I don't have an example of that here. Later in this video I do though. The nearest pi bond is right here. This other one's too far away. So roll this over. I think of this like being on a door hinge. So if this is a door and you're looking from the ceiling down onto the floor and you want to shut the door, you just kind of close it like this, right? You swing it on a hinge. I imagine that's what you're doing with the pi bond. You swing it over, so now the pi bond is here. And that carbon, which was missing its 4th bond, now gets a 4th bond. So this carbon's happy, 4 bonds, it's stable, it's neutral. But at the expense of the carbon right over here, it no longer has a pi bond. So now that's the carbon that has a plus charge. And to get all the resonance structures, move 1 pi bond at a time. So this pi bond on the left side moved. Now it's time for the other pi bond move and swing it over like a door on a hinge too. So it goes right here. And the carbon that used to be positively charged now has its 4th bond. It's satisfied. But this carbon's like, whoa, where'd my pi electrons go? Yeah, sorry, buddy. You're helping out the whole team here. Why don't you hold on to this plus charge for a second until we swing the pi bonds back and forth and spread that plus charge around the ring. Cool. That was step 3. Step 4, write the word base with a couple of dots. That represents a lone pair. On my exams, you do not have to give the chemical formula for the base. I got the caption here down here says that if you're doing bromination, FeBr4 minus is the actual base. It's a lone pair on one of the bromines that's going to grab this hydrogen. But on the exam, there will be a base somewhere in these reactions. You don't have to identify it. Just say word base, write out BASE, lone pair, start your curved arrow on the source of electrons, in this case on the lone pair. And you're saying, hey, lone pair, go grab an H. And we're not gonna have to draw that product, but if you wanted to, it would look like this. Don't have to draw that. But we need a source of electrons. Remove this hydrogen as H plus, because these electrons don't travel with the hydrogen. They stay behind. Curved arrow represents that. Kind of swing the door shut to finish, what is the word? Trying to restore aromaticity here. So we need the Huckel number to be 6. So now we have 6 pi electrons, and the final product is now aromatic. Cool, that's the mechanism, yay. Let's use this mechanism to try and understand why some groups are ortho para-directing, whereas others are meta-directing. Also, in the same mechanistic explanation, we get a sense of why some are activating and some are deactivating, right? Because those are the two things that directing groups do. They influence the rate of the reaction, and they also determine the position of the incoming group. They actually identify, what's the word? Regiochemistry. They control regiochemistry. Regio sounds like region, so the location of where groups go. All right, let's look at one of the kings of the orthopara directing groups, right? No carbons, halides. The first no is for nitrogen representing an amine. O of no is oxygen representing an alcohol of phenol. Okay, so what we're doing here is showing, is it our second step? Whatever step we're doing the resonance structures of the mechanism. So we're actually saying, hey, to phenol, let's add some nitric acid and some sulfuric acid and put a nitro group onto phenol. Okay, so in a situation where everything's random and the nitro group might go anywhere, what would the resonance structures look like? Okay, let's go to the top. If the nitro group goes ortho, so the nitro group is ortho to the phenol, right? Side-by-side carbons of the benzene ring. You're gonna end up with these 4, not 3, 4 resonance structures. So, right, so we said, hey, this is the carbon that had a pi bond, but the pi bond connected nitro to that carbon, generate a plus charge here. And then we roll this plus charge, this pi bond over to here. We get plus charge over here. And then we move to get the third resonance structure, because we always expect 3. Move this pi bond over 1, shut the door, and we get the other structure. So you'll get the, the 1, 2, 3 resonance structures minimum that we get in electrophilic aromatic substitution reactions. However, if you go back and inspect all the plus charges, so here's a plus charge on this carbon in the first structure. If an adjacent atom has a lone pair, the lone pair can opt to come down to create a pi bond. And that creates 3 bonds of oxygen. Not ideal, right? Remember honc, H-O-N-C, 1, 2, 3, 4. Oxygen prefers 2 bonds, but you're familiar with the hydronium ion. Oxygen can have 3 bonds. It's possible. And so if this is a valid resonance structure, and what's cool about it is that the carbon that used to have a positive charge because it only had 3 bonds, now gets its 4th bond. It's neutral. Oxygen, yeah, it has to bear the positive charge because it's making too many bonds, 4 bonds, and it didn't have 2 lone pairs. Now it only has 1 lone pair. So that's destabilizing. That oxygen has 3 bonds and is positive when it's electronegative. It wants to be negative. However, in the overall scheme of things, you now have a fourth resonance structure. And in general, more resonance structures make the entire molecule, the entire intermediate, more stable. Ooh, and if it's more stable in a mechanism, that allows a reaction to proceed faster. It's easier to do if these resonance structures are stable. And in fact, this fourth one, the new one, is the most stable among all four resonance structures. So bonus, not only do you get a fourth resonance structure that helps stabilize everybody, the one you're creating, the extra one, is the most stable among them all. You know why it's more stable than the others? There's an extra bond. All the other resonance structures only have 2 pi bonds, but this one here has 3. And more bonds is more stable, right? It goes back to the idea of what's more stable, what's stronger, a single bond, a double bond, or a triple bond. The triple bond, there's more bonds. It's holding the atoms tighter together. I think of it as ropes. If you have to separate 2 atoms and it's triple bonded together, you have to cut 3 ropes, 3 bonds to break them apart. That takes a lot of work. So more bonds, more stable. Go down to the bottom and look at para attack. Okay, so the nitro group goes para, goes to the other head of the table. And then, so this carbon that attaches the nitro group used the pi bond that used to be here. There it is, it's right here. This is the pi bond that got used to attach the nitro group, generating a plus charge right over here. And then that's our first resonance structure. Roll that pi bond over, shut the door, get the second resonance structure. Then this pi bond moves over. I guess they're showing the arrow here, but moves the plus charge over here. And here's our third resonance structure. Our minimum of 3, at least 3, sorry. And then go back and inspect all the resonance structures. Okay, so let's look at this first one here. Hey, any lone pairs on the adjacent atom to this plus charge? Nope, there's a hydrogen, a carbon, nope. How about this one? Yes. Adjacent to this plus charge, there's an oxygen, next atom away, has a lone pair. Lone pair come down, create that third pi bond, making this the most stable resonance structure. It's a fourth one. 4 resonance structures are more stable than 3. Cool. So both ortho and para can create this fourth resonance structure that has extra stability. However, if the group, nitro in this case, but it could have been any of the reactions, if nitro group goes meta, well then, what did they do? They moved the pi bonds. That's confusing. Start again. Okay, if I wanted this resonance structure, then this pi bond should have been here. And you can see, no, it didn't do that. So who made this graphic? It wasn't me. But maybe I shouldn't complain because I didn't have to do all the work of creating it. It's not going to stop me from complaining. Okay, start again. Let's nitrate phenol from this structure, and we want to put it meta. So if we're going to put it meta, this is the pi bond that creates the bond to the nitro group. And yeah, this carbon right here is going to lose its pi bond, become positive. Roll the door over, roll that pi bond over, put it here, plus charge is over there. Do it a third time, this pi bond slides over and plus charge goes down there. Now inspect your resonance structures. That's telling me I got to end soon. Sorry, thought I silenced it. Look at your resonance structures with the plus charge, and on this carbon with the plus charge, no adjacent atom with a lone pair. This one, nope, no adjacent atom with a lone pair. And this one down here, nope, no adjacent atom with a lone pair. We got our 3 minimum, and there are no more. 4 resonance structures are more stable than 3. So nature just doesn't choose the meta. You don't get nice stable resonance structures like you do if it goes ortho or para. And look at that, 50-50 in the lab under certain reaction conditions. That's kind of cool. There you go. So that's the main idea. If you want to just end the video now, you got the main idea. Let's look at some other examples. For those of you who want more info or just more examples, can be helpful. Let's take toluene. Where's that on our orthopara, or is it a meta director? Right? No carbons, halide. No carbons, halides. And then right here, a Above this are activating. Carbons, like a methyl group, is weakly activating. So this is going to speed up a little bit relative to benzene. Okay, so what's happening here? Well, same set of resonance structures. We're just changing the alkyl group to a methyl group. However, methyl doesn't have a lone pair. So if it goes ortho, so the top first, and the nitro group goes ortho next door to the methyl group, plus charge is here, right next to the methyl, but the methyl doesn't have a lone pair to create that nice fourth resonance structure. The alcohol and the ether, as well as the amide and the amine, all those atoms have lone pairs. They do create that fourth resonance structure. Carbons, like the methyl group, can't. So because it doesn't get the fourth resonance structure, it doesn't activate it a lot. The fourth resonance structure helps a lot, and it's super stable, more stable than the others. That makes it more activating, easier to do the reaction. Because this one doesn't get that fourth one, it doesn't activate it, doesn't speed up the reaction that much, but it does activate it. How is it activating? Let's classify the carbocation. What degree is this carbocation? Primary, secondary, or tertiary? Well, talk to the carbon. Hey, carbon, how you doing? Not good. I only have 3 bonds. I got the stupid plus charge. Help me out. Yeah, that's the resonance structure's job. But let me talk to you right now. How many carbons are you attached to? I got one up top, and I got a second one over here. I'm a secondary carbon. I'm a secondary carbocation, CC plus carbocation. This one, secondary. Ooh, this one, that's most stable. Tertiary, yay. And you should know, and you do, tertiary carbocations are more stable than secondary. So nature says, yeah, let's go ortho 63% of the time. In the lab, that's actually the product ratio, because we can make this tertiary carbocation as one of our 3 resonance structures. If you go meta, well, the plus charge skips over this tertiary carbon, and the plus charge is never there. It's always secondary. That's not so nice. But if you go para, 34% of the time, that's what will happen with toluene under nitration. The plus charge can arrive at that tertiary carbon, and that's a more stable carbocation. It's interesting that you still get 3% of the meta. That's not enough to say, ooh, I need to draw that on an exam, and I need to include it. No, that's not a major product, 3%. No, just ignore that. That's an impurity, essentially. But it does kind of attest to the fact, because it's weakly activating, a little bit of meta sneaks in. But on exams, we'll have to recognize that C, no carbons, halides. The methyl group is ortho-para directing. We're only required to draw the ortho and the para products. And that's a much greater excess than the silly meta, which we're going to ignore. What else we got here? We got chlorobenzene, no carbons, halides. So this is an ortho-para directing group, but it's weakly deactivating. Okay, so you get the same situation. Chlorine does have a lone pair. So just like phenol that we saw in our first example, when the plus charge arrives next door to the halide, a lone pair can pop down here. Okay. Honc, H-O-N-C, 1, 2, 3, 4. The H stands for hydrogen, but also stands for halides. Whoops. The halides prefer 1 bond. This chlorine is making 2. That's not so nice. That's destabilizing. Also, I don't quite understand this. Oxygen is more comfortable with extra bonds than the halide is. Oxygen is more electronegative than chlorine. But for some reason, when the halide has a double bond, whether it's chlorine, fluorine, bromine, or iodide, I'm just not as happy. So yes, this 4th resonance structure is the most stable because, again, we have 3 pi bonds, whereas the others, there's only 2 pi bonds. 1, 2, 3 pi bonds. That makes it the most stable. It's just not as robust, as stabilizing as when this is a nitrogen or an oxygen. And so, in fact, maybe due to electronegativity, although it's hard to argue that point. For some reason, again, nature's making the rules. When you go in the lab, you find out chlorobenzene reacts slower than benzene. So for some reason, the chlorine group is deactivating it. Gosh, what's the term for this? Induction. There's an induction effect. If for those of you who want some words to explain this, right? Scientists love putting new terms on every new idea. The electronegativity of the chlorine is sucking out the electrons, pulling the pi bond electrons towards itself because chlorine is more electronegative than carbon. And so that's oftentimes cited as the reason for the halides deactivating nature, is that they're inductive. They pull out, they withdraw the electrons. Like I said, I'm uncomfortable with that because doesn't oxygen do the same thing? Well, in some cases it does, but here it's not. Phenol is very reactive. So this is very much more stable than when it's a chlorine. Okay, so I'm confused by that. But nature, she plays the rules, so I just got to accept it. And just remember, no carbons, halides. And I get through. All right, what do we have here? Benzaldehyde, an aldehyde group. No carbons, halides. Carbon stands for methyl groups, pure carbon groups, alkyl groups, or a benzene ring. I don't have that. I know there's a carbon in the aldehyde group, but there's also oxygen. This is a meta-director, which you know to be strongly deactivating. It's going to slow down the reaction. In fact, if we're trying to do Freer crafts, it shuts it down. But we're not doing Freer crafts, we're nitrating. And that still runs, it just runs very slowly. So what happens? Well, it's your same resonance structures if you say, hey, remember we talked about the meta-directors being grumpy, sitting at the table of 6 people, 6 chairs rather. This one says, hey, I don't want you sitting next to me. Well, what if nitro says, the heck with you, I'm sitting next to you? Well, nature's not going to like that because the plus charge sits right next to the aldehyde group. And what's the charge on this carbon, the atom next to the plus charge? It's positive. Oxygen is slightly negative, more electronegative than the carbon. And this carbon bears a slight positive charge. And if the nitro group goes ortho to the aldehyde group, that'll create a positive charge on the atom next to a plus charge. You have adjacent positive charges. What do like charges do? They repel. Right, so this poor bond is in jeopardy of breaking. That's really destabilizing. So nature's going to avoid that because in one of her resonance structures, you get to a point where, whoa, we got these adjacent positive charges that are going to repel. It still happens 19% of the time in the lab. That's interesting. If you create the para isomer, nitro goes far away from the aldehyde group, you still have a resonance structure where a positive charge is adjacent to the partial positive charge of the aldehyde group. And that's really destabilizing. 9% of the time in the lab that happens. So 72%, okay, that's much bigger than these numbers. That's the major product. That's why we only draw on exams. That's why we only draw the meta product when we have a meta director on a benzene ring. Because the plus charge bounces around the ring and misses the aldehyde group. You don't get those adjacent positive charges. And so this set of 3 resonance structures is much more stable than the other 3. Cool. I think that's the end. Thanks for bearing with me. Hope that was helpful. At the very least, on exams, recognize that you need to include these 4th resonance structures. You'll get 5 resonance structures if you have a molecule. Let's put one on here. If a molecule has another atom with a lone pair, right? So if you have 2 directing groups, every time plus charge lands adjacent to lone pair, you can create another resonance structure. There you go. All right, that's enough for now. I'll see you on the discussion board.